We are going to be talking about covalent molecules today. And covalent molecules are when you have bonds between non-metal atoms only. Starting off, the reason why this is important is because the 5 major greenhouse gases in our atmosphere are all covalently bonded molecules. Those 5 are ozone, nitrous oxide, carbon dioxide, water, and methane. We are going to kick off the conversation about covalently bonded molecules with what's called a Lewis dot diagram or Lewis dot structure. The Lewis dot structure shows you how many valence electrons each element has within a group using dots. The trend is that the group number corresponds to the number of valence electrons. So if you're in group 1, you have 1 dot or 1 valence electron. If you're in group 4, you have 4 valence electrons, therefore you have 4 dots. And you notice if you look at, say, nitrogen, oxygen, fluorine, and neon, you can see that there are only 2 dots per side of the element. So you can have a max of 2 dots per side, for a total up to 8 valence electrons in the noble gas group. So let's talk about how these nonmetals bond to form covalent molecules. For covalent bonding, the nonmetals bond together through a sharing of valence electrons to complete the octet rule. This is differentiated from an ionic bond because in an ionic bond you have a cation giving a valence electron and an anion taking a valence electron. So you have a give-take. In covalent bonding you have sharing. As an example, carbon's electron configuration, 1s2, 2s2, 2p2. The 2s2, 2p2 are the valence electrons. Therefore, it has 4 valence electrons and it would get 4 dots for the Lewis structure. Fluorine, 1s2, 2s2, 2p5, the 2s2, 2p5 are the valence electrons. That's a total of 7 valence electrons, so it would have 7 dots in the Lewis structure. Both need to have a full valence shell. Because they're both nonmetals, they will share their valence electrons to do that. So here's what carbon would look like, and then this is what fluorine would look like. So fluorine is missing 1 electron. There is one exception to this. Hydrogen only needs 2 valence electrons to complete its, it's called the duet rule versus the octet rule. It's still a full valence shell. So please note that hydrogen can only have 1 bond when we get going on the Lewis dot structures. All right, so let's talk about fluorine a little bit. And let's bond 2 fluorine atoms together. On your periodic table at the very top, you have a list of what are called diatomic molecules. Diatomic molecules are when a non-metal atom bonds with itself to complete the octet rule. Fluorine is an example, so it's F2. They each have 7 valence electrons and they both are going to need 1 more. So if you draw out your 2 fluorines with 7 valence electrons each, what happens is they will come together to share those 2 center electrons to complete each other's octet rule. So you can see the fluorine that's circled now has 8 valence electrons. The other fluorine has 8 valence electrons. And whenever you have 2 dots between elements, you change them to a line to show that they're bonded together. So a line represents 2 dots. So this is what fluorine as a diatomic molecule would look like when it shares 2 electrons with another fluorine atom to complete the octet rule. That is F2, or a diatomic fluorine molecule. So now let's look at the carbon in fluorine. So we already said that carbon has 4 valence electrons and fluorine has 7 valence electrons. So let's start by drawing our carbon with 4 valence electrons, 1 dot on each side. Fluorine will come in on the right side to bond to fill the 2 electrons in for carbon. Now fluorine has 8 valence electrons by sharing that 1 electron with carbon. Another fluorine will come in on the other side it now has 8 valence electrons by sharing that electron with carbon. Same on the left side. Fluorine will come in, it now has 8 valence electrons. Lastly, on the bottom, another fluorine will come in, and it now has 8 valence electrons. Carbon, by sharing its electrons with the fluorine atoms, also now has 8 valence electrons because it's sharing with the fluorines. And if you're changing those center dots to lines, this is what the atom would look like. This is called carbon tetrafluoride. So now all elements in this structure have 8 valence electrons. You notice how the lines are only between two elements, and then you keep the dots on the outside where you have unbonded electrons. All right, so here's some rules. You have to take the total number of valence electrons in an atom. And then after you're done drawing your structure, you have to make sure that that total is still there, and I'll show you what that looks like. There are some exceptions. For polyatomic ions, you have polyatomic anions such as carbonate or CO3 2-. That 2- tells you that you need 2 extra electrons. And if you have a cation, which is a polyatomic ion, like ammonium, NH4+1, you have to remove an electron, and I'll show you an example of that. Predict the arrangements of the atoms. This means that you have to figure out which element goes in the center. As our example on the last slide, you had the carbon in the center. That's a prediction that you're going to have to make. Generally, if you have carbon in a molecule, it goes in the center. Hydrogen can never go in the center. After you predict the arrangement of the atoms in the molecule, start by making single bonds or one line between each pair of atoms, and that one line represents 2 electrons. Arrange the remaining electrons to satisfy the octet rule for every element involved. Place electrons in pairs. These are called lone pairs. As an example, the fluorine atoms on the previous slide all still had 2 electrons on each side of the atom. Those are considered lone pairs. If you have too few electrons, say that not every element in the compound has 8 valence electrons, what you need to do is you need to rearrange the electrons to make that happen. Sometimes if you have 4 extra electrons, it can form a double bond. If you have 6 electrons, it can form a triple bond, and I'll show you an example of that as well. Once you have your structure done, you have to go back and check, are all of the electrons used, and have all of the atoms had 8 valence electrons around them to complete their octet rule, with the exception, of course, of hydrogen, which only needs 2 electrons. All right, so let's do some Lewis dot structures, and I'm going to use the greenhouse gases as examples. The first molecule, CH4. Carbon has 4 valence electrons. Each hydrogen only has 1 valence electron. There's a total of 4 of them, so that's a total of 4 valence electrons. So I have the 4 from the carbon and the 4 from the hydrogen. That means I need a total of 8 electrons shared between, evenly between each atom so that everyone has completed the octet rule. And remember, hydrogens only have a duet rule, so they only need 2 electrons. So I'm going to draw my carbon in the center. Generally, the first element is going to be in the center. There are exceptions to that. So carbon has 4 valence electrons. And then there are 4 open sides here. So each side of the element needs to have 2 electrons. So I'm going to put a hydrogen here with 1 electron, a hydrogen here with 1 electron, a hydrogen here with 1 electron, and a hydrogen here with 1 electron, because they each have 1 valence electron. Whenever you have paired or 2 electrons between 2 elements, it becomes a line. So this is going to look like that. So each line represents 2 electrons. So if you look at the carbon, it has 2, 4, 6, 8 electrons around it. So the octet rule has been completed for the carbon. And then each hydrogen only needs 2 electrons, and 2 electrons are represented by 1 bond, so they have also completed the octet rule. So I've used 8 electrons. Every element has completed the octet rule. The next one, carbon dioxide, CO2. Carbon goes in the center. It has 4 valence electrons. And because there's only 2 oxygens, each with 6 valence electrons. That's a total of 12 electrons. So I have 4 electrons from the carbon, 12 from the oxygens, that's a total of 16 electrons. So I need to make sure when this molecule is done that there are 16 electrons. I'm going to place an oxygen on either side of the carbon for symmetry. And each oxygen gets 6 valence electrons, so 1, 2, 3, 4, 5, 6. Another oxygen over here, 1, 2, 3, 4, 5, 6. You notice how my carbon has unpaired electrons. What I'm going to do is I'm going to erase these electrons and put them in the center so that they're now paired. So now I have a bond between my oxygen and my carbon here and an oxygen and carbon here. But you notice that my carbon only has 4 electrons around it. So what you have to do is you have to take electrons from the outside elements and put them in on the inside. When I do that, I'm going to form double bonds. So you take from the outside and you put them on the inside. So now, if I were to redraw this, I have oxygen double bonded to my carbon, double bonded to my oxygen, and these dots or lone pairs come with them, like this. And so now I'm going to cover up my oxygen and count if 8 valence electrons are surrounding the oxygen. So I have 2, 4, 6, 8. 2, 4, 6, 8. My carbon, 2, 4, 6, 8. All of the elements in this atom in this molecule have 8 valence electrons, and I'm going to go back in and make sure that I have 16 to make sure that I did it right. So I have 2, 4, 6, 8, 10, 12, 14, 16 electrons. So this is perfect. This is called a double bond. So carbon dioxide is double bonded on the carbons to complete the octet rule. The next one, oxygen or ozone, has 3 oxygens. Each oxygen has 6 valence electrons times 3 is a total of 18 valence electrons. So again, I'll check at the very end to make sure that that is still true for my molecule. So I'm just going to draw 3 oxygens in a row. 1, 2, 3. They each have 6 valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So now that I have this, I'm going to go through and make sure that everything has 8 valence electrons, and if they don't, I'm going to move electrons until that happens. So this oxygen on the left has 2, 4, 6, 8. So I'm going to redraw that with a bond instead of dots between my paired oxygens. So that's good. So my oxygen is good, so it's going good so far. This oxygen in the center has 2, 4, 6, 8 electrons. Beautiful. So this one has a bond over here, and then it has these unpaired electrons or lone pairs on the top and the bottom. So those come with that. And then this oxygen over here only has 2, 4, 6 electrons. So that's no good. So what I'm going to do is I'm going to steal from the oxygen next to it. I'm going to put those in the center to form a double bond. And then that oxygen still has those 2 up top and the 2 down below, so those come with it. So now I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everything has completed the octet rule, and now I'm going to go back through and make sure that there are 18 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. It's okay to double bond one side and not the other. You could have also drawn it like this, with the double bond on the other side. It's kind of a mirror image. These are called resonance structures. Resonance is just a way of drawing the same thing but a different way. So there's options, so it's flipped. Next one, H2O. Hydrogen can never go in the center, so I'm going to put oxygen in the center. It has 6 valence electrons. Each hydrogen has 1, so that's a total of 2 valence electrons, so I need 8 electrons when this molecule is done. So I'm going to put oxygen in the center, and then 1, 2, 3, 4, 5, 6. The reason why I left The unpaired electrons on either side is so that I can put the hydrogens there. So you kind of have to project what you're going to need. And each hydrogen has one electron, so that's going to form a bond there. One electron, that's going to form a bond there. And so this is your water molecule. So it has unpaired electrons up top, unpaired electrons down below. And I need to make sure I have 8 electrons, so I have 2, 4, 6, 8. Beautiful, everything has completed the octet rule. Hydrogen, the duet rule. Last but not least, N2O. So nitrogen is going to go in the center, and I'm going to put a nitrogen on, so I have 1, 2, 3, 4, 5, and nitrogen over here with 5, 1, 2, 3, 4, 5, so I made them look exactly like each other, and then an oxygen over here, 1, 2, 3, 4, 5, 6, so my oxygen has 6, each nitrogen has 5 times 2, that's 10, plus 6 is 16 electrons. So I have 16 electrons here, however, I see that there are unpaired electrons. I'm going to immediately erase them and put them in the center together to form a double bond, like that. I also see an unpaired electron here and an unpaired electron here. What I'm going to do is I'm going to move this electron all the way over here. Remember that we're sharing electrons, so these electrons will move around until the molecule has 8 valence electrons in all of the atoms, until everyone gets what they need. So now I'm going to go through and make sure that I have 8 electrons. So this nitrogen has 2, 4, 6, so that's not good. This nitrogen has 2, 4, 6, 8, that's good. And the oxygen has 2, 4, 6, 8. Perfect. So this nitrogen is the only one that hasn't had the octet rule completed. So what I'm going to do is I'm going to steal from the center and create a triple bond. Nitrogen is the only element that we're going to be working with that triple bonds. Carbon can also triple bond, but for our purpose, nitrogen is the one that's going to triple bond. So now I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So you may be wondering, like, how is she doing this? How does she know to do this? All I'm doing is making sure that everything has 8 valence electrons, and I abide by the total number of electrons. That's it. You just move them around until it works. So I need to make sure I have 16. 2, 4, 6, 8, 10, 12, 14, 16. Beautiful. This is done.